Okay, so taking a quick look at our schedule here, notice that quiz 4 is due today, so make sure you put that in your folder before you go. And today we're going to talk about section 8.1, areas and volumes. Things that are coming up, project 4, the Gamma project is due next class, and I will assign project 5. So today we're going to learn how to measure area or volume of an irregularly shaped object by slicing the object up into easy to measure pieces. All right, so I just mentioned that the Gamma project is due next class. Okay. Project 4. Problems 5 and 8 from the Gamma project are particularly tricky. There is a YouTube video with some hints in there for questions 5 and 8. So I did put a direct link to it in Moodle. So in Moodle, our Moodle site, under Project 4, there's an extra link that says Gamma Project Hints. Okay, there's about 20 minutes. The first 21 minutes or so of that video walks you through questions 5 and 8, okay, which are the hard ones. Okay, so I'll let you do that on your own, and then move into our lesson. Okay. So remember that our definition for the area under a curve was the limit of a Riemann sum, right? We just sliced things up into rectangles, took the limit as the width of the rectangles went to 0, and we got and defined that to be an integral. All right, so we can convert certain Riemann sums into corresponding integrals, and we're going to use that technique to help us find areas and volumes today. All right, so we're going to find the area of this figure, this triangle. Right? We could find the area of a triangle just because we know the formula for the area of a triangle, right? So what's the area of a triangle that's got a height of 3 and a base of 6? 9. Yeah, 1/2 base times height, right? So for a triangle, this is not like the most useful technique, but this technique can be applied to things we don't have formulas for. So that's why, but we'll start with a triangle because we know what the answer is supposed to come out to. All right, so we're going to slice it up. Right, we're going to slice it up. We're going to write a Riemann sum where we add a bunch of rectangles together, and then we're going to convert that to a definite integral. All right, so we're starting at this end right here, and we're defining x to be the distance from this point along the base. Okay, so we pick some random spot along the base there, and we're going to say that that's a distance of x, like to right here. And we're going to call the width of a random rectangle. So we're basically slicing this into a bunch of little rectangles here. Right. We're going to take our triangle, cut it into a bunch of little rectangles, and then we're going to let the width of the rectangle go to 0. So we're just going to look at a typical rectangle, one typical rectangle. So the area of, I'll write it out in words here, of one typical rectangle. Okay, so I'm just going to draw 1 on here. This rectangle right here that's pretty much been given to us. One typical slice. It's a rectangle. What's the area of a rectangle in general? How do you find it? Length times width. Okay, what's the width of this rectangle? Delta x. Yeah. So all of my rectangles are going to have a width of delta x. So I'll have area is going to be length times width, and then length is going to be something, but width we know is delta x. All right, so the length we could also think of as the height of this rectangle. Now, all these rectangles that I'm going to draw along here, they all have different heights, right? It varies. So I've already defined a variable x to be the distance along my base. So if I called this y, that could represent the height, the varying height of my rectangles. I have to call it a letter because it's varying. All right, so let's just call it y for now. But this is a single variable calculus class. We hate it when there's more than one letter. So I would like to maybe write y in terms of x somehow so that I don't have two letters, right? So if I call this y, this is x, remember? So I have a little purple triangle here. Just going to copy it down here, whose base is x and height is y. And then I have this big triangle in pink, whose base is 6 and height is 3, right? What's true about those two triangles? They're similar triangles, right? So you have to remember a little bit from maybe a high school geometry class about similar triangles. What's true about similar triangles? The corresponding sides are proportionate, right? So I could do height to height equals base to base, right? So I could say 3 is to y as 6 is to x, something like that. And then if I solve this for y, you get 1/2 x. So 3x equals 6y, divide both sides by 6, you get 3y equals 1/2 x. All right, so the area of one slice is going to be y times delta x, but y is really 1/2 x. All right, so I have a generic area for one slice, but really I want to take a whole bunch of those slices and add them all up. Whole bunch of slices and add them up. So just to remind you, we're taking a bunch of rectangles, adding them all up. Okay. So let's take n of them. Say I'm going to take n. So I'm going to say the area total of my whole triangle is going to be approximately the sum where I take n rectangles. Every rectangle is going to have an area that looks like this. So it's going to be 1/2 x sub I times delta x. And I is going to go from 0 to n. And that's an approximation, right? If I take n rectangles, slice this thing into n rectangles, it's going to be, the way I drew it, it's a little bit of an overestimate, right? So how do I make this exact? Yes, and close. N has to approach infinity, yeah. N is the number of rectangles, so you either let the width of the rectangles go to 0 or the number of rectangles go to infinity. And then the other answer was a definite integral, which is the symbol we use for when you take the limit as n goes to infinity. All right, so my total area is exactly equal if I take this Riemann sum and take the limit as n goes to infinity. I goes from 0 to n, which is actually the integral of 1/2 x. So remember, when we translate from Riemann sums to integrals, you drop the sub i's, and delta x becomes dx, because as n goes to infinity, the width of your rectangle goes to 0. So delta x becomes dx because it's infinitesimally small. Okay, now I just have to put some bounds of integration on this thing. So my variable is x here, right? X is starting down here, and we're moving it. Each x represents the place where I'm drawing a rectangle. So I'm starting it here, and I'm moving it along this base. So if this is 0, what is this point right here? 6. So let's go from 0 to 6. I'm stacking up these rectangles from 0 to 6. And now we can just evaluate this integral. Take an antiderivative of 1/2 x, and what do you get? 1/4 x squared, evaluated from 0 to 6, which is 9. Seems like a crazy way to get the area of a triangle. But like I said, it's a useful method when you don't know a nice formula for the shape you're trying to find the area or the volume of, like in our next example. Okay. But any questions on this method so far? So step 1, you just look at the area of one slice. Just look at one typical slice, then you add a bunch of them up and translate it to a Riemann sum. I mean, translate it to an integral. Sure. The 0 to 6, where did those numbers come from? So I looked at my variable of integration as an x. So I went back to my picture and said, okay, what the heck did I make x again, right? And x is the distance from this endpoint to this endpoint. It's labeled in my picture. Can you see that little x right there? Yes, but the x is a variable, right? It moves. So it's the distance from this endpoint to whatever rectangle I'm drawing, right? So I drew it in one little place to show, for example, this rectangle, the distance is x. But for this rectangle, right, this is x, right? So x, the smallest x can be a 0 because it's the distance from this point to whatever rectangle I'm drawing. Yes, yes, where you add up all the possible rectangles. All right, let's do one more example. So this one's a little bit different in that I'm finding volume this time and not area. So I'm trying to find the volume of this irregular shape. We'll set up the integral. We're not going to do the antiderivative and plug in. We'll just use our calculator once we have the integral set up. All right, so this is some sort of semicircle base solid, right? So if I want to find the volume of this thing, I'm going to slice it up into slabs. So you can see that it's already got a typical slab right here. So this is a typical slab, and we're going to pretend that each slab is perfectly rectangular, okay? So there aren't those little bends in the edges there. Perfectly rectangular slab. So let's say the first thing I want to do is find the volume of a single slab of this thing. And the shape of that thing is like a box, right? It's just a rectangular prism. And how do you find the volume of a box? Length times width times height. So let's write that down. Okay, and then the volume of my slab. Again, I only want to have one variable in here. So one of these things is delta y according to my picture. Which one? Height. Yeah, the height of this slab is delta y according to the picture. So this is length times width times delta y. So now I need to somehow write length and width in terms of y or just a constant if it never changes. Okay, one of those things never changes. Yeah, yeah. This distance right here is always 10, no matter how high up my shape I go. It's always 10. So let's call that the width. So I'm going to replace my W with a 10. So the last thing I need to figure out is my length, right? So this will be length. That's width. All right, so the length. Got to be a little creative here. I'm going to erase everything I've got in the picture so that I can draw clearly here. So I've got delta y. I would like to write length in terms of y so that my only variable is y in here. So if I put a little point here, and I would like to know this distance, and this distance is labeled in my picture already as y. Okay. Do I know this distance? Yeah, what is it? 7. How do I know it's 7? It's the radius of the circle. Yeah, this is the center of the circle, and I've been given that the radius is 7. So that's a 7. And let's call this x, the distance I'm looking for. Okay, so I can use the Pythagorean theorem to get that last length there. So I'll write that up here. So x squared plus y squared is 49. So x is the square root of 49 minus y squared. But x is really only half the length of the slab, so I got to double it when I put it in my formula here. So finally, I can write the volume of my slab as length, which is 2 square roots of 49 minus y squared times 10 times delta y. Length times width times height. Only variable that shows up in that formula is y. You can use whatever variable you want. Sometimes we use y and sometimes we use x, depending on how we're stacking things, whether it's horizontally or vertically, as long as it's only one variable. All right, so there's the volume of a slab. So now if I want the volume of this whole solid, I just have to add up a bunch of slabs, right? So I would say the volume of the whole solid is approximately what you get when you take a sum of n rectangles where each, or n slabs, where each slab has this volume, 20 square roots of 49 minus y sub I squared times delta y. So y sub I is just the height of each various slab, right? So there's one slab drawn in this picture, but I actually have n of them, each one at a different height, y sub I. And then to get the exact volume of the solid, take the limit as the number of slabs goes to infinity. Which is actually an integral. And we drop the sub i's, and the delta y becomes a dy. So I have 20 times the square root of 49 minus y squared dy. And now I just have to figure out what the bounds of integration should be. So I go back to my picture. My variable is y, and y is what's changing. I'm stacking up these slabs from, what's the smallest y can be in this picture? 0, like the very bottom slab here, right? I'm very good at drawing. The very bottom slab is at a height of y equals 0. And then what's the very highest slab? What's its height? 7, right? Because that's the height of the whole shape, right? So I'm going to integrate from 0 to 7. I'm stacking up these slabs starting at a height of 0 up to a height of 7. And then I'll just have my calculator calculate this integral for me. I could calculate this by hand, but just to save us a little bit of time. So math, function integration, my function is 20 times the square root of 49 minus x squared. I'm using x because I don't have a y button. It'll come out the same. Oops. Yeah, that's right. Okay, comma x, my new variable of integration instead of y, comma 0, comma 7. And I get about 769.7. All right, so it was the same process as the one we did with area. First, get the area or the volume of a typical slice, then add up a whole bunch of them and turn it into an integral. Already got this? Okay. All right, one more example. This is finding the volume of a solid that has known cross-section. These are typically hard problems, these known cross-section problems. Just so when you come across one, don't get too frustrated. I want to find the volume of a solid whose base is the region inside the circle x squared plus y squared equals 4, and whose cross-sections perpendicular to the x-axis are squares. Okay, so we have to be able to picture this thing. So again, I just told you I'm an excellent drawer. I can't draw this. I can't do it. Maybe somebody else could come up and do it, but that's okay. I'm going to try to sort of describe it by waving my hands at it. And then I have a nice Mathematica picture to show you. All right. So the base is a circle in the xy plane. Circle of radius 2. So this is the base of my solid. And then you're going to imagine this is a 3D solid. So the rest of it like pops out of the board. Okay. So this is its base. This is like the bottom of your solid. And then its cross sections are squares perpendicular to the x-axis. So I would draw like a little line here. And that's going to be, then I would create a square coming off of that out of the board, right? So I have equally length sides and I make a square. And then I have them like all along the circle. I know it's hard to picture. So I have a good picture. Hold on. Okay, so here's my base. It's a circle, right? Base is a circle. And then the cross sections perpendicular to the x-axis that coming out of the board are squares. So it makes this funny looking, I don't even know what that's called. Where are the squares? Oh, hey, I can turn it. So there's the base, right? That's the bottom. And then you can see the square cross sections. So what wasn't quite a circle? It's definitely a circle. Like in certain orientations, it doesn't look like a circle because it's being drawn on a two-dimensional surface. Yeah. But the base is definitely a circle. And you can see I sliced it up along the circle here, or Mathematica did, right? And then we built squares coming off of each of those lines. And it made this cool shape. A what? A half of an eclipse? What's an eclipse? Ellipse? Oh. Oh, no, I don't think it looks like that because it's got these sharp edges, right? An ellipse is like a football, right? Okay, that looks like part of an ellipse, yeah. But then, so yeah, if you look at it this way, it does look like, but then when you turn it, you go, oh, that's not a football, right? That's a weird looking football. It's got like these sharp edges. Yeah. All right, so anyways, let's find the volume of it. So every slice, we're going to use the same process as before. We're going to find the volume of a single slice, add up all the slices, and then translate it to an integral. So each slice is a square, right? So even though I can't draw this thing, I know that you build it by building squares on this circle. So you take a chord of the circle, build a square off of it. Square. Okay, so each volume of each slice. Volume of a slice. Okay, so volume of, again, each slice, we're going to have sort of a rectangular prism or a box, right? So each slice is going to be length times width times height. But because this is a square that I'm building off of here, length and width are the same. So we'll just do length squared times height. And then height is just the delta x. Yeah, let's call that delta x. And let's say if 0 is right here, we'll have the distance from the origin to the rectangle I'm drawing be x. All right. So if height is going to be delta x, then I need to be able to write the length, which is this distance, in terms of x. Okay. And I actually do have, if this is x, then this is y, right? And I have an equation that relates x and y. Right, just solve that thing for y, and I know the height of the rectangle. So I know that y is the square root of 4 minus x squared, but then I have to double it because that's y and that's also y. Double it to get the whole length. Okay, so my length squared is going to be 2 times the square root of 4 minus x squared. Square that because I have to do the length times the length and then times delta x. So that's the volume of a single slice. Let's just simplify it quickly and make our lives easier. When I square a product, you're multiplying this 2 and this square root. When you're squaring a product, you just square each piece. So this becomes 4 times square root. They just cancel. So that becomes 16 minus 4x squared when you distribute. I'll write it in the next step. All right, so the volume of the whole solid is approximately equal to what you get if you add up all of these squares. Okay, so I'm going to add up all of these squares. Let's go from I equals 0 to n. I'm going to have n squares. And each of those squares with a little bit of thickness, so each of those slabs is actually going to have area 16 minus 16, 16 minus 4 x sub I squared times delta x. But that, if I is starting at 0, then I actually need to double that, right? Because I started in the middle here, and I have to double it to get the left half of the circle. So we'll put a 2 there. All right, so then to get the actual volume of the solid, the exact volume, I take the limit as n goes to infinity of 2 times my sum and then that turns into an integral. So that's 2 times the integral of 16 minus 4x squared. Delta x becomes a dx. And then my limits of integration, I defined x to be the distance from the origin to my rectangle that I'm drawing. So the smallest x could be, you could integrate from -2 to 2, but then I would drop that 2. Yep. Instead of, I'll integrate from 0 to 2. Both are totally fine approaches. Yeah. All right, so that's a quick antiderivative, and plug in the bounds, and I believe you get 42 2/3. Just to save us a little time, I won't go through calculating the integral. All right. I hate generic formulas. It's written down here, but we just did the whole problem without a formula, so don't even worry about it. Let's look at number 8. The basic procedure for using slicing to find area or volume. Draw a typical slice and label your diagram. Write the area of or the volume of one slice. Make sure that your formula for the volume of one slice has only one letter in it. Write out the sum of all the areas of n slices. Then write the actual area by taking the limit as the number of slices goes to infinity. Translate to a definite integral, and then calculate the value of the integral. All right, that's it. You try some.